Hello, dear friends. Welcome to my channels. Yeah, today discussions is quantum field theorem and proving no-others theorem and symmetry. Okay, symmetries and no-others theorem in QFT. Okay, so friends, you have to remember what is symmetry before no-others theorem, and this topic is very important for QFT. Okay, and also physics. Noether's theorem is very important for physics and quantum quantum field theory. We are going to be able to find information about our theories that would have been very difficult or maybe impossible to access otherwise. Okay, so a symmetry of the theory is defined to be a field transformations by which Lagrangian changes at most by a total derivative such that the action remains invariant, and thus the equation of motion are also invariant. Okay, so example, spherical symmetry. If you do the rotation right, just rotate, you have same equation of the motion. So we have used some aspect of symmetry. Now the theorem deals with continuous symmetry. Okay, suppose we have a continuous transformation which is internal, that transforms the fields according to phi I xi. Okay, x mu. Okay, we can write this way. Okay, we can write this way, that phi I x mu transforms phi I x mu plus del phi I x mu. Okay, this is Taylor's theorem, Taylor's and Maclaun's theorem. Okay, so at first we discuss what is Noether's theorem. Every continuous symmetry gives rise to a no-ether current gamma. Okay, gamma superscript mu, such that del mu and gamma mu is equal to 0 upon use of equation of motion. Okay, so this is the formula. So example of no-ether's current are, we can get global phase transformations, space time translation, and where you can get energy momentum tensor. Space time translation, you can get energy transformation tensors. Okay, and derivation of energy momentum for real scalar Lagrangian. So in classical physics, Noether's theorem states that there is a conserved current for every invariance of the classical action under a continuous internal or space-time symmetry transformation of the fields. This theorem also allows for a iterative method to construct invariant actions called Noether's method. Okay, current is going to be conserved, of course, should be valid upon use of equation of motion, which is in what we call on shell. Okay, yeah, we will go into that later, and it is important that you take that concept into account. So on shell and off shell, okay, on shell and off shell, we are going to start using it every now and then, because it is going to pop up more and more and more as we go into more advanced topic here. So continuous symmetry equals to time reversals and conserved quantity. Okay, so now I will prove Noether's theorem. Okay, so let's start proof. Okay, proofs of Noether's theorem. So okay, phi I is equal to, so similarly phi translate to phi. Okay, I can write this way: phi translate to phi translation plus epsilon del phi plus order of epsilon square. Okay, and L for Lagrangian, similarly Lagrangian tends to L plus epsilon del L. So del L, now we have to remember del L is equal to del mu f mu. Okay, variation of Lagrangian is going to be derivative of the f quantity. Okay, derivative of the f quantity. So Lagrangian, this is the del L means variation of Lagrangian. Okay, so del L is equal to mu f mu equals to del L by del phi into del phi plus variation del L by del into del mu phi into del mu phi. Okay? So keep in mind that you can exchange the order, of the variations and the derivatives. Okay, so this is the variation of field. Del phi equal to variation of field. Okay, now Lagrangian intensity. Now we can write this portion. Now you can say that del mu phi, del L divided by del mu phi equal to is Lagrangian intensity. Okay, Lagrangian intensity. So we can write del mu is equal to into del L divided by del mu phi into del phi. Okay, so this is called Lagrangian intensity. Lagrangian intensity, and this is called variation of phi. Variation of phi. Okay, equals to del mu into del L into del into del phi. Okay, simple chain rule. Okay, and it can be written as del L into del mu Lagrangian intensity into del mu okay, just changing the differential mode. Okay, I can write this way, del into del mu phi. Okay, so you see that this portion is equals to, it is this, we can write del into del del mu phi into del mu phi equals to del mu into del L divided by del into del mu phi into del phi. Okay, so it is minus del mu into Lagrangian intensity del L del mu phi into del phi. This is the value. Okay, this value. Now I give this equation number. Okay, my equation number is, my equation number is 1. I am putting this value, in here. Okay, this value I am putting this. I get this value, this equation I just replaced. Okay, I am plugging this value in here, equation number 1. So what then I get, the value is del mu. Okay, del mu f mu. Okay, del mu and f mu is equal to del phi, so equals to del L by del phi into del phi plus, just putting the value, this value I am just putting del mu into del L into del mu means Lagrangian intensity into del phi, the variation of the phi. Okay, here is, okay, error is, yeah, I can write this way. Okay, no problem. Bracket is, okay, bracket is including both. Okay, bracket is including both. Okay, minus del mu into del L into del phi, variations of phi into del phi. Okay, so this is my total work. Now you can So del mu and del phi f mu. So now we can write this way, that del mu into del l into del mu phi into del phi minus f mu equals to del mu into del l into del mu phi into del phi, okay, minus del l by del phi into del phi. So this is the very simple this equation, because you will, this is this part and this part, okay, you just change the sign, okay, so you get this and you just change this, so you get this portion, okay. Now you see that this is Euler Lagrangian. It can be written this way. It can be written this way. It is 0 because it is Euler Lagrangian. Okay, Euler Lagrangian on shell. This is Euler Lagrangian all shell variation. Okay, on shell variation currently apply is the symmetry, which means of course that we have not changed the equation of motion. And what are the equation of motion? This equation of motion is equal to 0. Okay, so we can write del mu into del l into del mu phi into minus f mu equals to 0. So it can be written this portion is equal to no either currents. This is j mu. So I can show easily j mu equals to 0. Okay, so Lagrangian density, the variation fields, this is called, this is Lagrangian density, this portion, and this is variation field, and this is the variation on the Lagrangian. So current that is associated to a particular transformation, two things that on radar. So this gives the following lemma. Okay, so this equation gives the following lemma. The lemma is continuous, every continuous symmetry whose associated no either currents goes to 0 as x space is tends to infinity and sufficiently fast gives rise to a conserved charge q, such that q dot equals to, means q dot means time derivative of charge equals to 0. So let's prove this theory. So start proof, because each proof is very important. So q equivalent to the integral over the space r into d cube x into j 0. Okay, so integral over the space r cube. Now j0 can be written it can be written integral over the space r cube d cube x into del t j0. How, friends? Because I just derivative of q dot, okay, means time derivative of q, time derivative of charge can be written this way, okay, j dot j, okay, so sorry, del t of j0. Now we know that by the Noether's theorem, del mu and j mu is equal to 0. So equals to del t into j0 plus del I into j I equals to 0, because this value is equals to this value. So we can write this way that del t j0 equals to del I j I minus del I j I. Okay, so this is the time derivative and this is the others derivative. So we can write q dot equals to integral over the space d cube x into del t j0 equals to minus integral over the space d cube x del I other derivatives into j0. Okay, so that is equals to 0 as x goes to infinity, as space x tends to mod of x tends to infinity, integral all over the space. Okay, and this is the special derivative, okay, del I j0 is the special derivative of j0. So another example, so I prove this theory. So another example is energy momentum tensor. Okay, so my another example is energy momentum tensor. So friends, we recall the theory. Which theory? We recall that we remember that j mu, okay, del L into del mu phi into del phi minus f mu. Okay, this is the energy momentum tensor. Okay, we are going to do just space-time translation. Okay, so it is just space-time translation. So we are just going to move through space-time. Just we get conserved current and conserved charge that is symmetric under time translation, then the energy is conserved. A symmetric under space translation, then the momentum is going to be conserved. Okay, okay, so at first I just want to say that Noether's theorem is an amazing result which lets physicists get conserved quantities from symmetries of the laws of nature. Time translation symmetry gives conservation of energy and space translation symmetry gives conservation of momentum, and rotation symmetry gives conservation of angular momentum, and so on. Okay, now this is the note. Okay, you have to note this portion. A symmetric under space translation, then the momentum is going to be conserved. Okay, I have already discussed. And global space-time transformation that goes like this. So we can say the transformation is going to be that our okay, discussions, global transformation. Okay, so we can write that x mu tends to x mu minus a mu. Transformation, a translation in space time. Then if we have this our field is going to transform into the field. Okay, into the field. This is the into the field, plus a mu but variations of field. Okay, so this is the plus a mu variation of field. This is del mu phi is variation. This portion is variation of field. Okay, of field. Okay, the field transforms. So here keep in mind that this is going to be variation of the field. So Lagrangian here is going to transform into the Lagrangian here is going to transform here into the now little algebraic trick. Okay, going to transform a is equal to same a mu into variation of Lagrangian. Okay, this is the variations of Lagrangian, variation of field. Similarly, it is variation of Lagrangian. So we little algebraic trick in a position to find the no either current. Once we have chosen which Lagrange intensity we want to study, so of course in the quantum field theory, so it can be written as a mu and little bit algebraic, so it is del mu and use contraction del mu nu l. Okay, instead of this value is equals to f mu. Okay, so now we used KGF theory. Okay, KGF theory is L equals to, we know everyone, I have already discussed in my video what is the KGF equation of the Lagrangian. So del mu phi into del mu minus m square phi square divided by 2. Okay, so this is the proof. So KGF theory we call energy momentum tensors, and energy momentum tensor which we call T So now energy momentum tensor. Energy momentum tensor can be written this way: T, okay, T mu nu, okay. So you can write is also T nu, also you can write in here also nu. Also you can write this way, no problem. I just write this way: T mu nu. Yeah, it is the, you can write also contravariant vectors, others mixed tensors you can use, no problem. So this formula can be written as, okay, in here L is equal to, I can write del mu, okay, del mu. So we get del mu phi into del mu phi, okay, minus mat mu nu capital L, okay. So L, now by the KGF equations, what we get? We get half into del mu phi del mu nu. So I can put this value, that this Lagrangian value, I can putting this Lagrangian value in here. So whatever I get del mu phi del mu phi, just matrix G mu nu, okay. You can write an L value, I am just putting it into del mu minus m square into phi square by 2. This way it can be written, okay. So lower the indices, lower and upper, I just write everything in upper indices. So we can write this way, that this is the value of t. So t 0 0 mu nu, this indices as 0 0, okay. 0 is here, 0 is time pace, yeah, this is the time. So this is stands to Hamiltonian. We get Hamiltonian value, just putting in here 0 0 and 0. So this value will be Hamiltonian. And when we putting the value t001, then we get momentum. So component of our space-time vectors, which is of course the time component. So we can be doing this translation in any of the four space-time: direction, right time, and their space ones. So we need to second index to tell us where the space are, okay. We doing this translation. So if we are doing the translation in the zeroth component, which would be time, that means that the symmetry here would relate to Hamiltonian, right, to the energy is relates energy conservation. So this part here should relate to the Hamiltonian. We are dealing Hamiltonian density. If we go to the other components, those would be the three space components, and those should relate to the conservation of momentum. So Hamiltonian density, this is the Hamiltonian density, H is equal to integration over this r cube d cube x t, this is the t00. So when I get that this value is integration over the space r cube dx, okay, d cube x, and t00 value is simple. When I just putting the 00 value, this is the phi dot, okay. In here you get it is phi dot whole square, and this part is equal to phi dot whole square. So from this equation, from this t mu nu equation, where if I putting the value of t square minus half into phi dot dot whole square minus del phi whole square plus m square phi square divided. So this is the space derivatives. Okay, that is del phi whole square is equal to space derivatives so phi dot whole square means time derivative squares. So we have the integral over all of space, and this would be, so phi dot whole square. Okay, now we get the simple calculation. So integral over the r cube d cube x is equal to half into phi dot whole square plus del phi whole square by 2 plus m square phi square divided. Okay, we can write this way. And now this positive proportion is called this phi dot equals momentum. Phi dot is equal to conjugate momentum. So we can write d cube x into pi square by 2 plus del phi 2 plus m square phi square divided 2. So this portion is equal to Hamiltonian. Okay, r cube into d cube x into Hamiltonian. This portion is Hamiltonian. So this is the value. Similarly, Hamiltonian intensity. This is Hamiltonian intensity. Now I can write Pi means energy momentum. Okay, Pi is equal to, we can write integral over the space r cube d cube x into t0 i, it can be written as t0 I value is from the equation momentum. We get del mu phi, okay, del nu phi minus, okay, minus g mu nu, okay, half into del mu phi into del mu phi minus m square phi square divided by 2. So this is the value. Okay, so now what we get, we just putting the value of the 0 and mu. So we get that integral over the r cube into d cube x into del 0 phi and del I phi. Similarly, we get g0 I into this portion g0 I and half into this portion. I just writing in here same value. This time is 0. Okay, g0 I. So we can write this way, that integral over the r cube into d cube x into pi del I phi. Okay, so minus, okay, the del 0 phi is equal to phi dot, which is equals to pi conjugate momentum. This is the conjugate momentum. A charge associated with space translation is indeed momentum that is carried now not by the particles, but rather by the field itself. So this is my no ethers theory. you have already seen that this equation I used in my Bose-Einstein statistics problem. Noether's theory is very helpful for everywhere in quantum field theory. Thanks for watching. I hope you can understand something